Hi, everyone. My name is Gavin. Sometimes online I go by Bodacious. And I work for Cleo. I should mention that we are hiring. So if you fancy working for the coolest fintech in the UK, scan that barcode. We have remote roles available. This is the universe. It's big. The universe is about 93 billion light years in diameter, and it's made up of about 10 to the power 80 particles. So we can say that it scales. It's old. We believe the universe is about 14 billion years old. And in that time, it's never had to be taken down from maintenance. It's never crashed. It's never exited with a non-zero exit code or anything like that. So we can say that it's a fairly robust process. And also in those 14 billion years, the universe has been constantly evolving, constantly developing new structures, new ways of being. And so we can say that the universe is flexible. And in this talk today, we're going to learn how to build one. At least in theory. I'd like to talk about some of the ways that nature builds and what we can learn from it. But I'm not going to use anything quite so complicated as the universe as my example. So my talk is called Objects Talking to Objects. And I'd like to go over some of the fundamental ideas from object-oriented programming. And I'll use that as a basis then to talk about process in complex and complicated systems, and then touch on some of the anti-patterns that I think violate these ideas. I'm going to use a kettle for my example. Sandy Metz gets bikes. I'm claiming kettles. So I really love object-oriented programming. I think it's really awesome that I have tools for building things that reflect the way that I think and understand the world. And that's by design. This here is the 1981 August edition of Byte magazine. This is where Smalltalk and object-oriented programming were first introduced to the world. And I'm going to be referencing some of the quotes. There's lots of articles in here about the philosophy and the design decisions that went into the object-oriented paradigm. So I'm going to be quoting from some of that today. But it's by design that we have this paradigm that reflects the way we think. The creators of Smalltalk and object-oriented programming wanted to create a language of description that serves as an interface between the models of the human mind and those in computer hardware. In other words, object-oriented programming lets us create code that's modeled on how we understand the real world. And the real world is made up of things, and we call those things objects. Just as a quick sidebar, quantum physicists and philosophers might try to convince you that there really is no such thing as objects, and it's all just a figment of your brain. If anybody tries to take that line of argumentation with you, I say steal their wallet and see how quickly they drop their convictions. We do, for all intents and purposes, live in a world of objects. So I want to look at some of the characteristics of real-world objects. So we can say that objects have identity, state, and behavior. I'll touch briefly on each of these. Identity is the unique selfness of a thing. It's the way that we distinguish it from other things. So if you think about a kettle, for example, I could have a kettle and it could be completely identical in all conceivable ways to your kettle, but we still recognize that these are two distinct things. My kettle and your kettle, or the kettle on the left and the kettle on the right. And that's because they have their own intrinsic, unchangeable identity. They have their own past and their own future. We recognize them as being distinct. And in object-oriented programming, we have the same concept. We could create a kettle class, create two instances of kettle, And they each have their own distinct ID. And in Ruby, we can ask, is kettle A equal to kettle B? And we get the answer false, even if all of the properties are the same. So an object is something that has a unique identity. We also say that objects have state. And state is just the word we use to describe the particular properties of an object. They can be static, but usually they're things that change over time. They could be abstract. A bill could be paid or unpaid. A door could be, there could be physical things, like a door could be open or shut. In the case of a kettle, we can say that it has temperature, water level, it can be on or off. And this is all information that we can find out about objects through interaction. And we can do the same thing in object-oriented programming. We can say that our kettles have a water level. We can say that they have temperature and whether they're on or off. We can model the real world. Objects also have behavior. In the real world, things have function and purpose, and we can do specific things with them. With a kettle, you could fill it, empty it, heat it. And again, we can model this exact same thing in object-oriented program. We can fill our kettle, we can empty it, we can turn it on and turn it off. And again, this is by design. This is something that the creators of Smalltalk and object-oriented programming called the reactive principle. The reactive principle states that every component should be able to present itself in a meaningful way for observation and manipulation. In other words, I should be able to grab my objects and ask them things about themselves and tell them to do stuff. Objects are not just physical things, though. We're not just talking about kettles and cars and doors or whatever. They can also be abstract things, too. We can be talking about time or units or money. And in Ruby, everything is an object. This is also a design concept from object-oriented programming. Ruby is one of the purest object-oriented programming languages in that sense. So even something like a hash, I could say that a hash has identity. We can take two hashes that have the exact same key value pairs and ask them, are you the same thing? And Ruby will tell us no. A hash has state. We can ask this hash, are you empty? And it'll say no. And it has behavior. We can ask our hash to do stuff. In this case, turn all of the keys into a string. And again, this is by design. If one part of the system were to work differently from the rest, then that part will require additional effort to control. So by making everything an object, we actually make the system simpler because there are no exceptions to the rule. So that's individual objects, but objects are not just isolated standalone things. Objects are actually made up of other objects. So a kettle is not just a kettle. Inside, it'll have things like heating elements and its power base, and those things are all made up of objects too, and it's basically objects all the way down. So just like in the real world, we start to bring lots of small, simple objects together to build more complicated things. We can do the exact same thing in object-oriented programming, and we call this the recursive design pattern, where things are just made up of more and more things. So we bring simple objects together and get them to interact to create more complicated objects. In the real world, physical things interact through various physical forces. In object-oriented programming, we allow objects to talk to each other through messages. This serves as a kind of metaphorical representation of real-world interactions. So messaging is what animates our objects and brings our code to life. I'm probably going to get my ass kicked for only having one slide about messaging and object-oriented programming talk, but that's all I have for now. To summarize that then, objects have three characteristics: identity, state, and behavior. And we can combine objects to make more complicated objects, and objects collaborate to become more than they are separately. So object-oriented programming is a powerful paradigm that allows us to build complex things out of simple things, just like we do in the real world. But the real world is infinitely complex. So we need a way to help us simplify and manage complexity so that our tiny minds can actually build something that's usable and maintainable. So over the years, we've developed principles to help us manage complexity, and we call these the 4 core principles of object-oriented programming. So these are abstraction, polymorphism, extension, and encapsulation. And I'll spend a bit of time describing these. So abstraction is capturing the essence of something by ignoring irrelevant detail. I believe this is where a lot of the art of software design lies. If you can learn to master abstraction, please come and teach me. But you could argue that all software is a form of abstraction. In object-oriented programming, we're usually talking about defining classes or modules and their interfaces. So if we go back to kettles, there are tons of things that you can say about a kettle. Kettles have nuts and bolts and serial numbers and power cables and many more things that I could fit on one slide here. But those things are not really necessary for us to understand what a kettle is or to use one. So we can simplify this, remove all of the unnecessary details, and focus on the things that matter to us. In this case, I have fill, empty, heat, and we can ask if it's boiled. I think that's a pretty reasonable abstraction of a kettle for most use cases. But one thing I like to do just to test my abstraction is to actually take the name away. And if I can squint and still recognize that it is the thing that it's supposed to represent, then that's usually an indication that you have a reasonably good abstraction. So the act of just creating classes and modules is a form of abstraction, but there's another way that we abstract, and that's to make specific things more general. See, there are other things that we can fill and empty and heat and ask if they've boiled, not only kettles. So by making the concept more general, we actually make this applicable to a broader set of problems. This can be more flexible, used in more contexts. Another way that we abstract is demonstrated in this code example here. So here we're creating a kettle, and then we're turning it on, and then we're checking its temperature, and we keep asking, are you 100 yet? And if not, I'm going to wait, and we turn it off. It's not totally clear why we're doing this or what 100 means or anything. You kind of have to know what a kettle is and how to use it in order to understand that. I would say this is a hidden abstraction, and what we want to do is we want to make abstractions more explicit, more concrete. Something like this is far easier to understand. So abstraction helps us to simplify and focuses us on what matters. We keep what's essential and we ignore the rest of the details. If you get this right, not only does it make your code easier to reason about and simpler, it also makes it incredibly future-proof and flexible because your abstraction can still be suitable even when a lot of the details change. But if you get it wrong, you'll often have to update the code and you'll be moving things around and it'll just never feel quite right. And that's why I argue that abstraction really is the art of software design. The next core principle is polymorphism. I once interviewed for a job, and the interview question was, can you define polymorphism? I panicked and said, it's when you're shaped like a parrot. Turns out polymorphism has nothing to do with parrots. It's about defining interactions based on what objects do rather than what they are. So looking at another kettle example, here we've got a class called a tea maker. This could be a person, a machine, whatever. And if you look at the code, kettle is explicitly defined here. Now, we could define a system like this, and it would work, but this design is fragile. and it's not very future-proof because it assumes the presence of a kettle. Now, a few months ago, my kettle broke. It's part of the reason why I've used it in these examples here. But when my kettle broke, I didn't just crash, I didn't raise an exception or anything like that. I went and grabbed a pot and I filled it with water and I heated the water on the stove and I was able to continue making my cup of tea. So you could argue that my personal tea-making process is a robust one. It's flexible to changes. We could update this code then to, what I mean to say is, personally, I don't care if I have a kettle. What I care about is I have a water heater, right? I care about having something that I can use to heat water, and kettle is an implementation detail. So we could update our code to represent that same way of thinking and say, I just need a water heater, and as long as my water heater knows how to fill up with water, boil, and empty, then I can make tea. And in this case, I can throw a pot in there, and yeah, as long as pot knows how to fill with water, boil, and empty, this system is resilient to change. So that's polymorphism. The next principle, I've called it extension. Often people say inheritance, but inheritance has become a bit of a four-letter word in software. People often argue that they prefer composition over inheritance. So I thought I would keep the peace by putting composition and inheritance under the same label called extension. Extension is adding new behavior to an existing abstraction by building on top of it without altering the original. And that last point there, I think, is what I want to draw attention to. So we eventually got a new kettle, and our new kettle has a digital display on it. I think this is the most useless innovation ever because I'm a software engineer. I don't care what temperature my kettle is. I just care if it's boiled or not boiled. But now we have a kettle with a digital display. If you look at my current abstraction of a kettle, it doesn't mention digital displays at all. Now, I could easily open this up and throw another method in there called digital display, and I've fixed the problem, right? But if you think about what that means conceptually, that means that I'm changing the definition of what it is to be a kettle. I'm effectively saying that all kettles now have a digital display, and that's not right. What if we could do something like this, where we create a new class called kettle with a digital or with a temperature display, and we extend our kettle abstraction. So it has all of the things that a kettle has, just with some extra behavior added in there. And for the composition folks, I've done the same thing with composition. The important point to highlight here is that in both of these approaches, we've added a new specialized behavior, a kettle with a temperature display, without altering the original abstraction. Adding a new specialization doesn't mean we have to change our original understanding of what a kettle is. We simply extend and build upon what we already have to create something that's more specific to our needs. This allows us to share and reuse and build upon what other people have created, adding new behavior without disrupting the system. The last principle I want to talk about is encapsulation. I think this is probably the most poorly understood principle. People often say that it's grouping data and behavior, but I think the emphasis with that encapsulation ought to be on information hiding. So encapsulation is hiding the information about an object's internal state and workings, exposing only a tightly controlled interface to the outside world. If you think about kettles again, when I use a kettle, I don't stick my hand into the water as it's boiling and try and measure the temperature. And similarly, I can't fiddle about with the heating element and the electrical wiring and all of that. That's all hidden away from me. All I really get to do is put water in and push a button. But beyond that, does anybody here know what temperature water boils at? Nobody? It depends is the right answer, yeah. So the temperature the water boils at changes depending on altitude and pressure. 100 degrees C is only sea level and normal pressure. Kettles have different ways of detecting whether or not they are boiling. Some kettles detect steam as it's coming out of the spout. Other kettles have a thermostat in the water that measures the temperature of the water. There's even a patent for an acoustic kettle that will listen out for bubbles and switch itself off when it's bubbling. I don't know what temperature my kettle stops boiling at. I have no idea. I don't even know which of these methods that it uses to detect whether it's boiled. All of that information is hidden away from me. And that's a good thing. That means that kettles are really easy for me to use. I know how to use different kettles. So if I go from having a steam kettle to a thermostat kettle to an acoustic kettle, it's all the same. I don't need to change anything in order to use them, because all of those details are encapsulated and hidden away. So a kettle encapsulates the knowledge about how it boils water. It hides that information about how it works internally and what parts it has. I have a code example here just to represent that. If we look at another tea maker example here, our tea maker is talking to our kettle, but it's talking to the heating element of the kettle. It's telling the heating element to start heating. And then it's checking the internal temperature. Once we get to boiling temperature, then it's telling the heating element to turn off. This is a complete violation of the principle of encapsulation, because our tea maker shouldn't know anything about the heating element. It should only know that the kettle can be turned on and will switch off when it's boiled. So that would be a much better approach, much better representation of encapsulation. So those are the 4 core principles of object-oriented programming. And just to summarize those for you, abstraction lets us hide details and keeps code manageable, but also flexible. Polymorphism lets us use multiple objects in new and different ways and allows for cleaner code and maximal flexibility. Extension allows us to introduce new behavior and allows for reuse without disruption. And encapsulation lets us hide implementation and protect internal consistency. It allows for flexibility, robustness, and safety. All of these principles work together to contribute to a code base that is more scalable, robust, and flexible. And this is the promise of object-oriented programming. If you follow these principles, the system you build should be maximally scalable, flexible, and robust, while minimizing the cost of future change and disruption. You might notice that I haven't mentioned process at all. If we're building complex systems using a lot of simple objects, where does the process live? And this is a question that I've studied for a few years now. Where is process defined in complex and complicated systems? So when I look at a natural complex system, I don't look at beehives very often, but beehives, galaxies, leaves on a tree, stripes on a tiger. In none of these cases is there a single place where these processes, these very complex processes, are defined. Rather, these processes are things that emerge from all of the individual parts or actors in these systems, all just doing their individual jobs. And the same thing is true of man-made things. If we think about kettles or the gears inside of a clock, a combustion engine, or even computer electronics, there's no single place, no single thing that orchestrates all of those individual parts and tells them all where they should go and what they should do. Instead, they all just interact with their neighbors, and the process is something that results from all of those interactions. When we're writing software, though, sometimes we take a different approach. We often want to define process in a single place, and we end up writing objects that become like process objects. And one of the most common patterns that I see in Rails these days for this is service objects. So if you're not aware, a service object usually looks something like this. It's a class that has a name that describes the process rather than the object or the thing. Typically, they have a single method, a class method, and it usually has a very general name like call or execute or do thing. An entire process is then defined within these objects, and sometimes we see result objects returned that'll tell us whether it did the thing or did not do the thing. When I see code that looks like this, I should say, when I see service objects, I think to myself, does this have identity? And the answer is no. I can never even get an instance of one of these things to talk to. They're very ephemeral. Does it have state? No. Again, the answer is no. They're stateless operations. You might argue that they have variables and things, but it only has transient internal state. Does it have behavior? Yes, it does a thing, but it's limited to a single one-shot command. I can't interact with one of these objects. I can't ask it about itself. I can't ask it to do different things. There are no meaningful descriptive messages that I can send it. And so these kind of violate that reactive principle that I mentioned earlier, where we can grab our objects and talk to them and ask them to do things. When I see code that is stateless and has only one method to call, usually called call, and it has inputs and outputs but no identity, I think to myself, that's a proc. And I've got another one. For me, that's all service objects are. They're procs that we embed in a class for some sort of syntactic legitimacy. But to me, service objects break the object-oriented paradigm. These are moments where we step out of object-oriented thinking and write procedural lists of instructions instead. What this really is an attempt to centralize process in a paradigm that expects process to be distributed. We're trying to do this in a paradigm that wants us to do this. This is the key point that I want to get across today, so I'm going to show you that again. We're trying to do this in a paradigm that expects us to do this. In object-oriented programming, process is not centrally defined, but it's something that emerges as a result of objects talking to objects. And so I think this is a bit of an anti-pattern. It violates a lot of the principles that we've just discussed. And I want to look at some of the issues that I believe these cause. So going back to our service object pattern here, this class has many dependencies. I count 6 dependencies, maybe 7 if you want to include the rational class there too. It has user, plan, subscription, payment, account, and result as its dependencies. That's not necessarily a terrible thing, but we generally understand that the more dependencies code has, the more reasons it'll have to change, and the more fragile this design is. Because this is an entire process, any new steps that we add to the process are likely to add new dependencies. So this is an object that will continue to complexify and grow as we change our process. This is a conceptual diagram to try to illustrate what I mean. Here we have a procedure object, a service object, and it has many dependencies. An object-oriented way to approach this problem might look more like this. But the number of dependencies is not the only issue here. If we look at the code again, we're talking to the subscription through the user, and then we're talking to payments through subscriptions through the user. And so we don't just have first-degree dependencies. We actually have transitive dependencies that are 2 degrees separated, sometimes 3 degrees separated. This necessarily breaks encapsulation because the procedure object has to know about the inner workings, the relationships of the second and third transitive dependencies. We've known that this is a bad pattern since the 80s. We call it the law of Demeter, and these service objects almost invariably force you to break that. So this is a system that is designed this way is, again, very fragile, very susceptible to have to change when any of these dependencies need to change. An object-oriented approach doesn't have transitive dependencies, and you basically shouldn't ever really have to have transitive dependencies if your code is well-designed and well-structured. I have loads of complaints here, but I'm going to pick one last one. If you look at the code here again, we are setting the subscriptions plan directly, and we're setting the amount based on the plan amount multiplied by some discount. That's how to create a subscription, really. And at the bottom here, once we are happy that the payment's passed, we're setting the status of a subscription to active, and we're setting it subscribed at timestamp to now. So that's really knowledge about how we activate a subscription. In other words, these are hidden abstractions. And I feel that this service object pattern, because it's an attempt to define the process centrally in this one place, they often have lots of hidden abstractions in them. This code really ought to belong in the models themselves. So conceptually, what we have is the service object asking lots of information back and forth between the object, rather than just telling the object to go and do the thing. We call this the tell, don't ask principle. Again, it's not new. So none of this is new. When C++ came out, people started to write what they were calling object-oriented code, and they would write long procedural blobs of code, occasionally talking to classes and using them as getters and setters for data. And Alan Kay, who coined the term object-oriented programming and is one of the creators of Smalltalk, he started to use the phrase real object-oriented programming to differentiate their ideas from what everybody else was doing. His main idea was that we should be building like nature builds. Martin Fowler, who was mentioned earlier, in 2003, he with Eric Evans wrote about something called the anemic domain model. They filed it under bad things, and you can read that for yourself, but what they're complaining about back in 2003 was that they saw lots of code where all of the business logic was written in classes called service objects, and they were only treating the domain models as places to get and set data. None of the business logic was defined in the domain models themselves, and so the domain model really had no detail in it at all. I've got links to all of this in my notes at the end, by the way, if you want to read it for yourself. So I want to give people some tips for using procedure objects or service objects. My first tip is don't. I'm not just saying that to be funny. If you find yourself about to reach for one of these, I would encourage you to stop and think, could this behavior belong in one of my models? And if so, put it there. If not, then it's likely that you are missing an abstraction from your domain model. Maybe there's a class that you haven't defined. And so you probably just want to build more of a specific domain model. If you treat your code as instances of objects that you send messages to, and they are well-defined abstractions with encapsulated behavior, service objects just become totally redundant because there's nothing to put in them anymore. You'll find that they evaporate if you properly apply the 4 core principles. If you still decide that service objects are the right tool for what you're doing, my advice would be to keep domain knowledge out of them. I would use these as very lean objects that know very little about the domain model, and treat them just as a sort of sequence of messages being delegated. If you can use dependency injection, that's probably going to be even better. And this allows the objects themselves to encapsulate the details of the process. And the service object then really just controls flow, similar to a controller action in that sense. My third tip is don't call them from other procedure objects or other service objects. This is one of the biggest smells that I see in Rails apps these days, is nested service objects. Sometimes you see a service object that calls a service object, that calls a model, that calls a service object. And so you're weaving in and out of different layers of architecture. It becomes really, really difficult to manage, and eventually you'll kind of grind to a halt. Changes will become very difficult and very expensive. If you decide that service objects belong in your architecture, I would suggest that you use them as entry points into the business domain. So calling them from a controller action or a worker might be a sensible place to do that. Putting all of that together then, object-oriented programming is a really powerful paradigm that allows us to build scalable and complex systems that are robust and resilient to change. Any patterns that we use that step out of this paradigm should be treated with skepticism. And process should not be centrally defined. It should emerge through objects talking to objects. Thank you.